For the second example, we need to just use the Colebrook-White equation to calculate lambda, or pipe roughness coefficient value. So we have like implicit equation at the top here. And remember, we can have like another equation to calculate the velocity here. And however, you can see for the like implicit equation, we can just estimate like the lambda on the right hand side and calculate the lambda on the left hand side, and iteratively replace the lambda on the left hand side in the lambda on the right hand side, and again calculate on the left hand side. Iteratively, we can just go ahead with this sort of things as long as the two consecutive lambda, calculated lambda, becomes converged, or the difference becomes less than the threshold. To have a like a first estimation, there's like the equation like here, written here. It's like the estimated value for the lambda, which is valid for the Reynolds value between 4,000 and 1 million, and relative roughness of like the 0.01, and claim to be accurate like the within 5%. So for a starting point, we can just use this equation. Let's look at the one example, how we're just gonna go ahead. For the previous example, example one, imagine for the pipe diameter 1.2 meters and with the discharge of the 2.672 cubic meters per second, we're just going to calculate the lambda. So to calculate the lambda and the required hydraulic gradients that we just need to just have, we first of all, we have like the diameter and the discharge. We need to have velocity. We just use a continuity equation. Continuity equation is like a Q over A. Q is like a 2.672 divided by A. A is like the area, like the for the circular cross section, pi diameter squared 1.2 meters squared over 4. Over 4 comes to like the top of the ratio, and the velocity here calculated as 2.363 meters per second. Once you just have like a velocity, we need to just calculate the Reynolds and the K over D. Reynolds is like a VD over nu. V is calculated here. D is like a 1.2 meters divided by nu. Dynamic viscosity is like a 1.005 times 10 to the minus 6. Is comes from the previous example that we said here that the previous example assumptions are in place. So Reynolds can be calculated 2.821 million. Is a dimensionless. There is no dimension for that. K over D can be calculated as this figure, like the 0.0006 divided by 1.2 meters diameter, and this is the result of the K over D relative roughness, 0.000500. And here, once we're just gonna have, we can just use this equation. But for the first estimation of the lambda on the right hand side, we can use this equation that we can have at the bottom right. So we just use that equation. We have like a K over D, we calculate, and we have like a Reynolds number. If you're just going to substitute the Reynolds, the lambda can be calculated as like the 0.0175. So if you're just going to have this one, we can iteratively calculate in that equation a lambda until it converges. And the SF can be calculated as by using the friction equation that we have. HF is like a lambda L V squared over 2GD. If you're just going to divide both sides by L, the left hand side is like a HF over L. The HF over L is like the hydraulic gradient, or SF. We can just write HSF. And on the right hand side is a lambda V squared. L has been cancelled out with the L that we divided on both sides. So lambda V squared over 2GD. Okay, so SF, or the hydraulic gradient, can be easily calculated. So lambda from the previous equation, we can just replace here, and V in the same from the previous calculations, and divide by 19.62 times D, or diameter, is like a 1.2. So SF can be calculated here. So this is like the hydraulic gradient. So if you're just going to replace it in the like the implicit equation here, you can easily see calculate the lambda on the left hand side, and iteratively try to just calculate the lambda on the right, put it on the right and calculate on the left, as long as they're just going to converge and the difference between two consecutive lambda is less than the threshold. If you're just going to carry on this one, eventually you can just going to get like the converge to the value of the lambda is equal to 0.0169. So that's like the value. And the hydraulic gradients accordingly can be calculated as like the 1 in 250. 1 in 250, as I said, if you divide this figure, reverse this figure, you can just see this calculation, this value, 1 in whatever length. So this is like the example 2 to just calculate the lambda.